Here's what we did in class after watching the first video on Intro to Power and Type 2 Error. You can follow along with the attached problem. We're continuing with the grocery store problem. What we did here was the write-up for a hypothesis test listed there. If you want to stop the video and look that over, make sure you're solid with all the parts to the write-up, that's great. But then what we want to do is use our understanding of the hypothesis test to move into power and type 2 error. But here's what's strange now. When we calculate power and type 2 error, we're doing this up front before we ever take a sample. It's part of knowing, oh, is our sample big enough? Are we running a strong enough test, a powerful enough test, so that we get the information that we need? So really, we never would do this after we took a sample and ran a whole test. We would do this ahead of time to make sure that the sample we take and the test that we run is going to be good. So what we want to do is we're going to assume the null is true. Somebody is going to have to give us an alternative mean. In this case, somebody in the know, some expert, said, hey, 285 is a big concern. What if it was 285? If that was the true mean, is your test powerful enough to detect it? In other words, what's the likelihood you're going to reject the null given that the true mean is 285? So we go back to the null in that sampling distribution and we find the critical sample mean that is 1.645 standard deviations above the assumed mean in the null. That is the critical value that we have to get past. So theoretically then, if somebody's going into this real population, they need to get past that critical X bar to reject the null and make the right decision. But we can use normal CDF to say, well, what's probably that we get less than that X bar, less than 278.2 if we're sampling out of this true population. So we get 0.086, that's just normal CDF. That means we have almost a 9% chance of getting a sample mean that's too small so that when we are running the hypothesis test, we get a sample mean down in there, we fail to reject the null, and we make a type 2 error. But you can see that 91% of the time, if this was reality, we'd get a big enough sample mean that we would be in the critical region for the test and we'd correctly reject the null. And right now the question is, well, how can you make power even greater? 91% is pretty good, but what kind of things can you do? The two most practical things to do would be to increase the sample size or to increase the acceptance of a type 1 error, the significance level of the test. So we rerun this power and type 2 error. Again, it's like we never really even ran a sample. We're doing this all up front. Now let's see, well, what if we took a sample of 120 out of this population? And again, we're going to assume that the true mean is equal to 285. Now what would the power be? Well, we recalculate the critical sample mean because now the standard deviation you can see is 3.65, where in the original problem it was 5 because we did 40 divided by the square root of 64. So the increased sample size gives us less spread, a smaller standard deviation, which means the 270 and the 285 are more standard deviations apart. This is really what's going to allow us to have a smaller chance of making a type 2 error. But all you have to do is follow the steps. Go figure out what sample mean is 1.645 standard deviations above the 270. That's 276.2. We know that that then would be the threshold we would have to get past if we were sampling from this actual population, and what's the likelihood due to chance we'd get a sample mean so small and we would fail to reject the null. Well, that's only going to happen 0.007 of the time. So in 99% of all samples, if this were reality, we would get a sample mean big enough and we'd reject the null and make the correct decision that the mean is greater than 270 seconds. Well, there's another way to increase the power of the test. And so we're going to go back to the original sample size of 64, but we're going to raise the significance level to 10%. We can live with a 10% chance of making a type 1 error. What that does is that now allows us to move the critical sample mean left. We don't have to be 1.645 standard deviations past the mean. We only have to be 1.28. So finding that sample mean, that's 1.28 standard deviations past, turns out to be 276. So now that's the threshold we have to get past in this sampling distribution that goes back to a standard deviation of 5, right? We'd take the 40 and divide it by the square root of 64. 40 divided by 8 is 5. So these guys are more spread out than the scenario where we increase the sample size. But we allow ourselves to only have to reach a z-score of 1.28. So in this case, there's a 96% chance that we will exceed the critical sample mean. One might ask, one can easily wrap their brain around the fact that, oh, okay, let's increase the sample size. That's a good way to increase the power. We'll get more accuracy. That's a good thing to do. You want to be careful about increasing the alpha level. Now, certainly if you increase the probability of type 1 error, you're going to decrease the probability of type 2 error and increase the power. But the question to ask is, can we live with a greater chance of a type 1 error? Because honestly, when we're going to run this test, we don't really pretend to know that the true mean is 285. So supposing we really have no clue, can we live with a 10% chance of making a type 1 error? And this is where we just use some common sense. The thing that AP will tend to test us on with regard to type 1, type 2, and power is to say, what are the consequences of a type 1 error? What's the consequence of a type 2 error? Which one seems worse in this problem? Well, in this problem, we could say, you know, if we fail to reject, or if we reject the null and make a type 1 error, then it's really not that bad of a situation. We'd be bringing on more workers during those times, which costs a little bit more money, but heck, the customers are happier, so maybe there's at least a bit of a benefit from that. We might end up losing a little bit more money, but it's not as dire as a type 2 error. A type 2 error is when we thought there was no big problem, didn't bring more workers on during those hours, and we're going to start losing customers and get a bad reputation. So type 2 error is more consequential in this problem. So I think we could definitely make the case for saying let's increase the probability of a type 1 error.